312, which is equivalent representation of trig functions. Okay, so I have put here the identities that we need to know. Now, these are not necessarily new because yesterday we talked about cosecant, secant, and cotangent, right? We had 1 over sine, 1 over cosine, 1 over tangent. It is also true that sine is 1 over cosecant, cosine is 1 over secant, and tangent was 1 over cotangent. So they are reciprocals of each other. So sine is 1 over cosecant, while cosecant is 1 over sine. Because doing 1 over something just flips it, right? Because cosecant, if we make it a fraction, right, 1 over that, dividing fractions, easy as pie, flip the second and multiply. It just flips the fraction that you have. So we need to make sure we have all of these memorized. We are going to have a quiz next week that will just be straight memorization of the trig identities. And it will say reciprocal identities, and there will be 6 blanks right there for you to fill in. And you will write these 6 facts down. Okay. We also need to know the quotient identities. And so we used this yesterday. We've already seen that tangent is sine over cosine, right? That's the y-coordinate over the x-coordinate. We probably used y over x more often from the unit circle, but y is sine, x is cosine. So sine over cosine. Cotangent is the reciprocal of that. It's flipped, right? So cotangent is cosine over sine. We talked about that yesterday as well. So these are not necessarily new things, but I'm putting them here. We must have them memorized. If you do not have these memorized, you can't do what we're trying to do. You have to know these facts because a lot of what we're going to be doing is like replacing one thing with another so we can solve a function there. These are called identities because they are always true. Sine of theta identifies as 1 over cosecant theta. Those are one and the same, right? So they're the same there. So we also have some new ones here. Okay. The next slide has your Pythagorean identities. Okay. And these are big ones. And it looks kind of complicated to solve. But let me show you where these come from. All right. Let me get my pen here. All right. Let's just pick a point on that unit circle. All right. And I'm just going to put a random point, not necessarily a point. And on that random circle, on that point circle, you've got an X and you've got a Y, right? And if you were to make yourself a little triangle right there, then this length right here, that would be your X coordinate. And this length right here, that would be your Y coordinate. And this would be a right angle. Right here. What would the radius of that circle be? If we're talking about the unit circle here? 1, right? Okay, so would you guys all agree that in that triangle, x squared plus y squared equals 1 squared, right? That is true. That's a pretty basic Pythagorean theorem that you guys probably all mastered already. So this is true. If this is on the unit circle, x equals cosine theta. Y equals sine theta, right? So I can replace that x with cosine of theta, and I can replace the y with sine of theta, and of course 1 squared is just 1. And then here, all they've done, they put the sine first instead of the cosine, but does it matter which one's first? Not when you're adding, so you could write it with cosine first if you wanted. And then they used the notation where they put the little square right here with the sine instead of in parentheses there. And so this is where this comes from, right? Just a triangle on the circle. Sine squared theta plus cosine squared theta equals 1. Now, the others look way more it looks complicated that we have these others here. But we can turn this first one into the other two. If you memorize this first one, then you can use some reasoning to figure out the others. So watch this. Let me show you how to get tangent squared theta plus 1 equals secant squared theta. I know that sine squared theta plus cosine squared theta equals 1. We're going to use that one a lot. That one should be one that's fairly simple for you to remember. If you went to my calculus class right now, I doubt they are going to remember either one of the tangent and cotangent ones, but I think most of them will remember sine squared theta plus cosine squared theta equals 1. We used it enough that it kind of sticks. So, sine on tangent is sine over cosine, correct? So, if I divide this by cosine squared theta, that's going to turn this into tangent squared theta. And I can do that as long as I divide everything by cosine squared theta. Right? So, sine over cosine is tangent. What is cosine squared theta over cosine squared theta? 1. That goes here. And what is 1 over cosine? Secant. Right there. So, if you have that first one memorized, you can get the second one just by dividing everything by cosine squared. Let's look at the bottom one. We're going to do something pretty similar. We've got sine squared theta plus cosine squared theta equals 1. On the other problem, we divided everything by cosine squared. This time, let's divide everything by sine squared theta. Okay. What is sine squared theta divided by sine squared theta? 1. That's here. What about cosine squared theta over sine squared theta? Cosine over sine is cotangent. And what is 1 over sine squared theta? 1 over sine is cosecant. I honestly don't even have the second two memorized all that well. Whenever I see something I think might be that, I kind of have to like picture it in my head. Oh, if I've got sine squared plus cosine squared equals 1, what could I do? Oh yeah, that's right. So if you know the first one, you can find the other two. On the trig identities quiz, you will have the Pythagorean identities. It will say Pythagorean identities. It will have 3 blanks there. And you will fill these 3 in. It is fine to have scratch work over to the side where, oh yeah, I knew the first one and I'm figuring out the second 2 for that. There. Now, the better you have them memorized, the easier it is to recognize them if they show up in one of these problems there, but you can just figure them out if you need to. All right, so let's look at some of the things you will be asked to do. Okay, so I'm going to start with one that's an equation. All right. This seems wrong. That 3x seems wrong. Maybe not. There's a chance I've got to change. No, I think, no, we'll be okay. We'll be okay. This one will work. All right, so the function f is defined by f of x equals sine squared x plus 1, and the function g is defined by g of x equals 3x minus cosine squared x. What is the x coordinate of the point of intersection of f and g? So this is just like we were doing yesterday, right? It's asking for a point of intersection. What should we do with these two equations? Set them equal, right? So like that first step is no different than what we were doing yesterday. We've got sine squared x plus 1 equals 3x minus cosine squared x. yesterday, well, I guess it wasn't really yesterday, 2 days ago, I said that we need, like, if we see squares, we need to move everything to one side and factor. But am I going to be able to do that if I have a sine squared and a cosine squared? If you have mixed trig identities, like you've got some are sine, some are cosine, or some are tangent, some are cosecant, you're not getting anywhere with that, right? We need to get all of them to be sines, all of them to be cosines, or possibly get rid of them altogether. In our minds, we have to have stored up the trig identities, right? So there's really a couple ways you can approach this. For this particular problem, I see a sine squared and a cosine squared, and we just wrote down, or we just looked at sine squared plus cosine squared equals 1, right? I do not have sine squared plus cosine squared, but could I make this turn into sine squared plus cosine squared somehow? I could just take this cosine squared, I could add it to the other side, right? So I would have sine squared x plus cosine squared x plus 1 equals 3x. And on these types of problems, it is pretty important that you show all of your work. They show up on the free response questions pretty often, and they're going to expect you to show your work, not just get an answer for that. So I know sine squared plus cosine squared equals 1. So I can replace sine squared plus cosine squared with 1. And I originally was like, oh, this is not going to work because of that 3x. But do we even have a sine squared or a cosine squared anymore now once we replace that? No. We just have 2 equals 3x. We can divide both sides by 3. And x equals 2/3 there. So you kind of have to have that vision of, oh, I can see, I can put these together. You're looking for where you could replace something with those identities. Okay, questions? All right, let's keep going. Okay, here's an example of something they may ask you to do. Again, free response section. The function f is given by f of x equals cosecant x over secant x. Write the function f as an expression involving only tangent and no other trig functions. So I've got cosecant over secant, which definitely is not tangent. Sine squared plus cosine squared is probably not going to be involved here because I don't see any squares, or at least it doesn't look like it immediately, right? So if I have cosecant and secant, those are my reciprocal functions, right? So probably what I need to do is change everything to sines and cosines, right? So I've got f of x equals cosecant is 1 over sine x. Secant is 1 over cosine x. Now I need to simplify this because they're telling me f has to be, I can only have a tangent. No, it doesn't mean it equals tangent itself. It could be like 2 times tangent, or tangent x plus 1, or, tangent squared. But it can't have sines and cosines in it, right? So I've got a complex fraction here. What do we do when we have a complex fraction? I think I heard it. Flip the second and multiply, right? So I could write this as 1 over sine x times cosine x over 1. And when I multiply those two things together, I'm out of room. I also don't know why this has started showing up and I don't like it. Actually, okay. So f of x equals cosine x over sine x. On these problems, very important you show your steps. Also very important that there is a logical process for your work. See how I kind of ran out of room and I drew an arrow? You need to do that. Your work, some of you have beautiful, like glorious, organized work that looks better than mine. And some of you look like a madman writing your work. Like, you know, whenever a mathematician like goes crazy in a movie and they just like start writing on the windows and the walls and everything's all over the place. That's what some of your papers look like. On these, it's really important that the grader can follow what you were doing. So you either need to work down, and then if you have to go back up, put an arrow, right? Or you need to work across with like arrows in between. It needs to be very clear. I went from this step to this step to this step, because they're grading your process, not just your final answer on this. It depends on how many points that part is worth on the like FRQ. If it's only worth 1 point, you wouldn't get partial credit. If it's worth 2 points, they might could give you 1 point, but not the other. A lot of the ones on the pre-cal exam are only worth 1 point. So you don't want, and you especially don't want to like risk it. Like if you know how to do the problem, you don't want to risk losing that point over laziness and not liking to write your work down, right? I get it. Like I skip a lot of steps if I'm just doing scratch work as well. But this is not scratch work. They are grading your work. I don't grade pre-cal exams, but like I grade calculus exams, and I am always appalled at the like handwriting and disorganization of some students. Like this is the only test that matters for whether or not you get college credit for this class, and you couldn't write legibly. It's eye-opening, really. I mean, I know some kids have bad handwriting, but you would think they'd do their best in this situation, and I think most of my students probably do, but well, not everybody. Some of them are bad. So here, now, what is cosine x over sine x? That is cotangent, right? So f of x equals cotangent x. Now, I think this is the most simplified answer. Like, this looks the best. But what did they tell us our expression has to involve? Tangent only. So how do we rewrite this so we have tangent? Because cotangent's not the same as, we can do 1 over tangent x. And then that would be our answer. And a lot of times on my notes or my worksheets, there's not a ton of room because I'm trying to like save space. On the AP exam, they give you a pretty good amount of room, so you should be able to fit. In fact, if you cannot fit your work, unless you write gigantic, if you can't fit your work in the box on the AP exam, you're probably not doing something right, because they give you a lot of space for that. So, but I would say the opposite's not necessarily true. Like if you barely fill up the box at all, sometimes that's okay, because they just go with like a standard amount of space for each question, even if it will not take much room. Mm-hmm.
On the exam, it's a derivative question that requires Pascal's triangle.
Yes.
Or something like that. You want us to write it on the question?
It is fine to write it on the question. I definitely do it like over to the side. I don't know if they give you scratch paper on the, see, I can't give my test, so I've never seen anybody take this test. So I don't know if they give you scratch paper on the free response section. I would say if they do, I would avoid using it, because you might be writing something on your scratch paper that was pertinent to what they were grading. So I would say yes, just draw it. I mean, obviously you don't want to make it too huge, but draw it over to the side if you need Pascal's triangle, because it does take up a little bit of room there. But But you'll have like a different box for each part. So whichever part you need that Pascal's triangle for, there'll probably be room to do it there. And then you may, the next part will have its own box too. So we will do a full length practice test in here, and I will try to print off like a practice answer sheet for you guys so that you can see what that answer sheet will look like, because they have those available so you can see like what it'll look like for that. All right, let's keep going. All right, we've got f of x equals secant squared x minus tangent x cotangent x. Which of the following is an equivalent expression for f of x? All right, so now things are getting a little crazier. If I look at my answer choices, I can definitely see that cotangent goes away somehow, right? There's no cotangents in the answers. There's a chance the secant squared stays, but not necessarily, right? See, this answer choice has a cosine pop up. That seems a little odd, but it can happen, so I don't want to totally disregard that one yet. So, if I see secant squared x minus tangent x cosine x, cotangent x. Now, if I'm thinking, like, you guys don't have these memorized well yet because I just gave them to you, right? I mean, these you should maybe kind of know, but we need to, like, know them really well. I do see, like, a secant squared. That equals tangent theta plus 1. So I might want to keep that in mind, right? Like, maybe that secant squared gets replaced with that, possibly. But it's hard to tell. So you're just going to, like, run through ideas. You might want to change this to tangent squared plus 1. I don't think it's going to get you anywhere immediately unless you deal with this tangent x cotangent x first. So there's a couple different approaches that you can take to this. Now, this is a multiple choice question, so they don't grade any work on multiple choice questions. So it's less important, but I think it's a good practice for us to try to do every problem like it's a free response problem, because it gives us that practice even if it's not. Let's try this. You got two options here. Tangent x is sine over cosine, and cotangent is cosine over sine. Or we could think of cotangent being 1 over tangent. Either way. I'm going to go sines and cosines. So tangent is sine x over cosine x. And cotangent is cosine x over sine x. Right, everybody okay there? What can happen with those two when we multiply them together? Sines cancel, cosines cancel. Everything cancels. What does it cancel to? What? 1. Very good. So it's not just gone, because what you're doing is you're dividing something by itself. All right, we got like sine x cosine x over sine x cosine x. So you're going to get minus 1. Not an answer choice, pretty close to B, but can I just flip subtraction? No, so that makes me think B's probably not it, because I don't have like a way of just flipping subtraction without doing anything else. So let's go back, that secant squared. Secant squared equals tangent squared theta plus 1. Maybe we could replace that. Let's try. So f of x would equal tangent squared x. We're doing x's on this one. Plus 1. So this is going in for secant, right? We still have a minus 1 over here. Oh, I think this is going to work, right? And then, so what happens with a plus 1 and a minus 1? Hey, guys. We got tangent squared x. Oh, Savannah, thank you. getting things. Add it to my trees up there. Okay, so tangent squared x, there's our answer. And these are definitely going to be calculator inactive, but let's just like get a picture of what's happening here. If I mean, there's no point in me like showing you how to solve this with the calculator because they're not going to give you a calculator on these problems. But let's just, I do think it is a good idea for, so, why is that not? Why is that not graphing? Do I need parentheses? Maybe I need to do it like this. We may abandon this effort here in a second. Why is it not graphing? Oh. It wants parentheses around these things. Okay, so here's like this crazy graph for this particular one. Let me give you guys the notes. Let's see. You guys will in class show me how to write that. Okay. All right. So, like if I graph the other ones, f of x equals tangent x cosine x. Oh, it does not like it if I don't put the parentheses around this right here. Not the same graph at all, right? But if I graph the one that's actually the answer, you see they're exactly the same graph. So this is the same function. We have just rearranged it to look differently. And on this particular one, it's a lot more simple, right? We've simplified that function. So we're like taking steps to replace things till we get something that's a little bit more simple there. But they are still the same functions. They will give you the same values out if you plug numbers in. Okay. And so for my seniors that just came in, we are looking at using trig identities to either solve equations or rewrite equations into equivalent forms. And so these are the ones, we really have already looked at these. And then I went through the Pythagorean identities as well. These are things we need to have memorized. So we will have a quiz next week. It won't be Monday. It'll probably be Wednesday, maybe Tuesday, maybe Wednesday. Definitely not Monday, though. Where you're just going to have to write all these down. We have to have those memorized. And at the first part of the video for this, I'll show you how to do that. Hey, John Carlo. Yeah, that's fine. If you want, you could like hang it on that back, you'll hang it on that back bookshelf right there on the knobs or something. That way maybe it won't get too wrinkled. There. All right. So, we'll have to have those memorized, and those are the things that we're using. Let's keep going. We've got f of x equals sine x secant squared x over cosecant x. We have to rewrite this as an expression involving tangent and no other trig functions. Do you guys see tangent anywhere in that? No tangents. And we're supposed to make a tangent appear. And we are supposed to only get rid of all the other functions, right? So any ideas? I do know secant squared is tangent squared x plus 1. That could come into play, but I'm not sure what to do with it after that. We could maybe possibly take that approach. Because I've done more of these problems, I don't necessarily think that's going to be our best bet there.
Are you, so like,
Yes, you are. Because if we have a fraction, so because like what this really means right here, that's a very good question. Will said, are we allowed to do reciprocals if there is a square? Yes. Not for like Pythagorean identities. We can't like, Pythagorean identities have to be sine squared plus cosine squared. We can't do that for sine cubed plus cosine cubed or something like that. Though Pythagorean identities have to be squared because Pythagorean theorem is a squared plus b squared equals c squared. Right? We can't mess with that structure. It's not a cubed plus b cubed equals c cubed or a plus b equals c. That doesn't work. But if it's just these problems right here, you're not adding or subtracting, not Pythagorean identities. What this means is secant of x squared, like that. So we can rewrite secant as 1 over cosine x squared, which means this is going to be 1 over cosine squared x. And in fact, that is exactly what I would do. Okay? So a good strategy to try on things like this, even though we're trying to get tangent, is change everything to sine and cosine. Okay? So sine obviously is already sine. So we got f of x equals sine of x. And then secant squared x, secant is 1 over cosine. So I can write this as 1 over cosine squared x. And you don't have to show the work that I just showed over here to the side. It is okay just to do this. And then cosecant is 1 over sine x. Now, I have a complex fraction, but I really don't want to flip and multiply yet because I have like 2 fractions in the top. Or not 2 fractions, two things in the top, right? But sine, I can put that over 1, like that. And so, if I multiply these two together, I would get sine x over cosine squared x over 1 minus sine x, like that. And now, anytime you have a complex fraction, you're probably going to need dividing fractions easy as pie. Flip the second and multiply. So sine x over cosine squared x times sine x over 1. Are you starting to see it? Anybody see where we're going? Because we got to get tangent. What do you think? Yeah, so when I multiply these 2 fractions together, sine times sine is sine squared, right? So I've got sine squared x over cosine squared x. And what is sine over cosine? Tangent. And you can, it's okay to do that with the square. So we can say sine squared over cosine squared is tangent squared x. Now, if they were not both squared, we could not do that. They have to have the same exponent, but we can write it this way. So f of x equals tangent squared x, and that is all tangents. Yes?
So, you can do it before and like simplify the design square with it.
Yes. Technically, here, Will, the top squared also, but 1 squared is 1 for that. So, but yes, there has to be a square. So if you're doing secant squared, it has to be 1 over cosine squared. You still have to have the square. Or if we, like here where we're doing sine squared over cosine squared, in order for that to turn to tangent, they both have to be squared. And it'll be tangent squared, not just tangent for that. You really came in here on the end of a lesson where you maybe lost 7. But we are working on either solving equations or rewriting equations using the first 2 slides on those notes, which have like our identities, our facts that we know about trig functions. Okay, and I've videoed it so you can go back and look at it. All right, let's look at 5. I've got cosine x tangent x equals -1, and I need to solve this for the unit circle, right? But can I solve things when I got 2 different trig functions? I could if it was equal to 0. I could set them each equal to 0, but does that rule apply when we equal -1? No. And I could move the -1 over, but am I going to be able to factor if I've got cosine x tangent x minus 1? Doesn't factor, so it won't get us anywhere there. So we're looking for some trig identities. And a really good strategy, if you don't know where else to go everything sine and cosine, right? We just like, those are the easier ones, we go back to those. So right here, if I say this is cosine x times tangent is sine x over cosine x equals -1. And notice how I kind of made cosine at the top, right? Because we could put that over 1 to make it a fraction. What can happen here? Those cosines can cancel. So now we just have sine x equals -1. Well, we did that a lot already, right? Where does sine of x equal -1? 3 pi over 2. Right here, those coordinates are 0, -1. So x equals 3 pi over 2. All right, we got one more we're going to look at. I think this is the last one, right? This one looks terrible. Now, on the other problem where we had a sine squared and a cosine squared, we like moved one over so that it was sine squared plus cosine squared and we could change it to 1. Is that going to work here? If I move one of them over, I'm going to have like sine squared minus cosine squared. Is that the Pythagorean identity? Does a squared minus b squared equal c squared? No. So that is not going to be an option here. But here's what we can do. Over to the side, I'm going to write this down. Let's use blue right here. All right, so I know that sine squared plus cosine squared equals 1. It's Pythagorean identity. It is fact. Okay. If I subtract cosine squared, I should have thetas or x's right here. If I subtract cosine squared theta from both sides, is this statement, I don't know why I just did that, is that statement still true? Sine squared theta equals 1 minus cosine squared theta. Should be, right? I just subtracted something from both sides. That's a legal math move. This is also a fact. It's not a separate identity because it just comes from the Pythagorean identity. But sine squared equals 1 minus cosine squared. It is also true if I take that same logic, if I have sine squared theta plus cosine squared theta, which is a fact, equals 1. If I subtract sine squared theta, then cosine squared theta equals 1 minus sine squared theta. This is a fact. Okay? I'm not going to have you list them as like separate trig identities because it's really just both still the Pythagorean identity that's been rearranged a little bit. So what this means is if I have sine squareds and cosine squareds and I want to get them all to match, I can use these facts to change. Now, let's look at the problem. Should I try to change everything to cosines or to sines? Or does it matter? Okay, why, Evan? That is true, but there's a bigger reason. A bigger reason. I can factor it because can I change cosine x to sine x? I cannot. Remember, Pythagorean identity has to be squared. A squared plus b squared equals c squared. Not a plus b equals c, right? That doesn't work. So I can't change cosine x. If it's not squared, you can't use Pythagorean identity. So since this has to stay, I want to change my sine squared x. So this is what it'll look like. I'll have cosine squared x minus cosine x plus 1. I don't mess with that side. Equals sine squared x is 1 minus cosine squared x. Now this is starting to look like the problems you were doing on the quiz and the problems you were doing the other day, right? So if I've got a quadratic, I move everything to one side. So I'm going to add the cosine squared x, and I'm going to subtract this 1 right here. So this is gone. I've got, what is cosine squared x plus cosine squared x? 2 cosine squared x. When you're adding, it's just like 1 and 1 gets added together to give you 2. You don't change the exponents there. Minus cosine x, and positive 1, negative 1 also actually cancels each other out, so I just have this. Now it's really looking like what we were doing the other day. What should I do here? GCF. We're going to pull out a cosine x. So we got cosine x times 2 cosine x minus 1. Alright, then we set each one equal to 0. Cosine x equals 0. That one's ready for the unit circle. 2 cosine x minus 1 equals 0. Add 1 to both sides. 2 cosine x equals 1. Divide by 2. Divide by 2. Cosine x equals 1/2. So now we're ready for the unit circle. Cosine is the x-coordinate. X-coordinate is 0 right here at 0, 1. So that is x equals pi over 2. Also right here, 0, negative 1. That is x equals 3 pi over 2. And then I need cosine x equals 1/2. That is x-coordinate right here, 1/2 root 3 over 2. And also right here, 1/2 root 3 over 2. So I would get x equals pi over 3 and x equals 5 pi over 3. Okay, questions?